Hello and welcome to GDC, and this is bringing 4K ray trace visuals to the world of Hitman 3, brought to you by Intel and IO Interactive. Briefly pause on the legal disclaimer before moving on to today's agenda. Basically, today's talk is split into three sections. I'll be covering the work we did to bring Hitman 3 to Intel's 12th generation core hybrid CPUs. Alexandra will then take over and talk about the work he's been doing on ray tracing that is coming to Hitman as part of an up-and-coming DLC. Then I'll return to cover Intel's XeSS, a deep learning based super sampling technique. So, your speakers for today are myself, Lee Davis. I'm a senior application engineer at Intel. I'm based in the UK and I've been working with game developers for the last 20 years.
Hello, my name is Alessandro Corso and I'm a senior render programmer at IO Interactive, and I've been the main implementer of the ray tracing backend in Hitman 3.
So, for the first part of the talk, I'd like to cover bringing Hitman 3 to Intel's 12th generation hybrid architecture. Back in 2011, last year, Intel introduced a new class of CPU, hybrid CPU, that combines two different core types onto a single SoC. Intel refers to these as our P cores or performance cores, which each have its own L2 cache. These are designed around single and lightly threaded workloads, where performance is critical. In addition to this, we have our E cores, built in blocks of 4, with 4 E cores sharing an L2 cache. This allows us to scale out the architecture for multi-threaded workloads. All the cores communicate through a shared L3 cache. The cores themselves share a common ISA, so the OS can migrate threads from one core type to another seamlessly. This does mean that the P cores do not support AVX512. From an OS point of view, all the cores can be enumerated using CPU ID or get logical processor information, with the extended version of that function also providing a performance rating for the core types. One thing I'd like to mention before we move on is Intel's Thread Director. This is a piece of hardware that sits between the cores and the OS. Its job is to monitor the instruction mix that's currently running and provide hints to the OS where best to schedule work. For example, if the Thread Director noticed a thread was very SIMD heavy, it would hint to the OS this is best scheduled on a P core. Likewise, if it detected a thread with a lot of user mode waits, it would hint this is best scheduled on one of the E cores, where it could wait in a more efficient state and free up resources on the P cores. So how does this map to gaming? Well, here's an XPerf trace from the game covering multiple frames. At the top we can see the very long running control thread, followed by the render submission thread. Both of these map very well to the P cores, where straight line performance is critical. In addition to that, Hitman has a very wide tasking system that can make use of all the available resources within the engine. So, for the next few slides I'll be talking about performance from the game, and we're using the Dartmoor benchmark. This benchmark is designed to be CPU heavy. It stress tests the game's physics system. While we're looking at something that is a pre-recorded demo, this very benchmark can also be done in an interactive manner, so you can actually do all of this destruction yourself. And it does represent things that can be done during the actual main game play itself. That was just a 20 section of the benchmark. Overall it lasts for over 2 minutes. And the benchmark itself is made up of very different scenes with their own unique workloads, combining both indoor and outdoor scenes. Probably the easiest way to describe the effects of hybrid on the benchmark is to start off looking at how the game behaves on a traditional 8-core system. So for this, we took an Intel 12th generation core and disabled E cores in the BIOS. But we did leave the L3 cache intact, so we can directly compare this data to a system running with the E cores. A couple of things to note. We have an orange line, which is the GPU timing. This is between 3 and 6 milliseconds per frame. And we have the blue line, and you can see the black line in the middle, which is a 10 frame moving average. And you can see the noise and how much variation we have frame to frame on the CPU. If we compare this to the same benchmark running with the E cores enabled on the same system, you can see the variation frame to frame drops significantly. Diving a little bit deeper into that, we take those frames and sort them, and we can see that the 90th percentile and above With the E-cores enabled, we are significantly faster, between 12 and 16%. In extreme cases, we saw over 20% gains. Overall, the benchmark is about 4% faster. I'll note that yes, it does appear that very, very fast frames appear a little tiny bit slower, about 1%. This may be noise, but there could be a few other explanations which we'll look into. So, why the frame-to-frame variation? This is a view from the game's in-game profiler. The top line represents the GPU, and we can see we're not GPU bound. The second line is the control thread, and you can see how active this is. And the final one is the render submission thread. You can see this is very busy, but we do have a few gaps. This represents 4 frames, with the first few frames taking about 7 milliseconds a frame, then a very slow frame for 10, and then a fast frame of 6. The thing to note that 10 millisecond frame, there is a large white block right at the start called simulation end, which is taking about 2.6 milliseconds. This is the game's physics. While the game is running at 165 FPS and about 6.5 milliseconds a frame, the physics is actually only being triggered once every 16 milliseconds. So it happens on average once every 3 frames. This leads to this average, slow, fast, repeating pattern. So, how do we improve the slow frames? Well, the first thing to note is the physics is actually triggered at the midpoint of the preceding frame. The actual white simulation end is while we're waiting for that physics to complete before starting the next frame, because we have to wait for it to complete to make sure there's no race conditions in other data structures such as the rendering. Diving deeper into what's actually going on in the physics, you can see that it is both widely threaded in parts, but also has a relatively lightly threaded broad phase section. As the physics workload increases and we have more active objects, this becomes the bottleneck. So we basically, for hybrid, rewrote that broad phase section. The game already statically grouped the various physics objects by region. What we now do is go through those regions and estimate, based on the number of active objects, how long they'll take to process. Then these are processed in parallel using the game's tasking system. Now, the interesting thing to note, by doing it this way and sorting them from most expensive to shortest, the game effectively dynamically balances across the different core types. It does not matter even if one of these more expensive threads happen to be scheduled on one of the E cores, because the P cores will finish earlier and then take additional tasks from the end of this queue. So everything dynamically balances to make the best use of the available hardware. This bears out in the results. Again, using that capture tool, we actually gather 30 frames at a time, and on a system without any E cores, we're spending 24 milliseconds waiting for physics to complete. With the E cores enabled, this drops to only 11. That 90th percentile I mentioned earlier, we drop from an average of 3.4 milliseconds of wait time to 1.5. So we're actually reducing the amount of time spent waiting for the physics to complete by 55%. This also partially explains why the very fastest frames appear slightly slower. We actually become slightly more render thread bound. The one other thing we want to mention is Hitman 3 does not use any hard thread affinities. The OS is free to move threads around based on their priority, quality of service and the Intel thread director feedback. So how does the OS go about scheduling threads across the different cores? The top graph represents a traditional system. For the first 8 threads, each thread will have its own physical core. For 9 to 16 threads, we will actually have 2 threads running per physical core. So we can see in Hitman, for 37% of the time, we actually have 2 logical processors sharing the same physical processor running a thread. So that render and control thread actually spends quite a large amount of its time having its resources contended with a different thread that is running in parallel. When we have the E cores, what the OS will actually do is, while the first 8 threads will again be scheduled to the P cores, the second 8 threads will actually go to the E cores. So up until we're running 16 threads, we will have one thread per physical processor. It's only when we exceed 16 threads that we start to pair up additional logical processors on the P cores. And you can see that it is a significant reduction from 37% utilization to 23%. So on a hybrid-based system, that control and render thread spend much less time having their resources in contention with an additional work inside the tasking system. The other thing to look at is how effective is the OS at keeping those critical threads on the P cores. And we can see here, if we look at the control thread, which is running for 96% of the time, for 95% it's on a P core. Same for the render thread. It's running for 87% and 85% of the time it's on a P core. Whereas the tasking system is actually well spread across both P and E cores. One of the main reasons for this is the OS actually looks at the duration that tasks are expected to run for and prioritizes long-running tasks on the actual P cores. So in the case here, both the control and render tasks, their average runtime is over 5 milliseconds, where the actual jobs within the tasking system, they average only half a millisecond. So the OS does a good job of keeping things onto those P cores for the critical threads. This is important to bear in mind. Doesn't so much happen in Hitman, but we've seen other titles where you have long-running background tasks. They may be low priority, but the OS detects them as being long-running and will prioritize those onto the P cores, which may not be the design intent. This is where things like the quality of service APIs can be really important, where you could mark a background task that may run for a long time, but not be time critical, to actually stay on the E cores. So, in conclusion, when we brought Hitman over to Intel's hybrid architecture, the first thing we looked at were bubbles on the P cores. The P cores are only going to get faster over time as we're able to make design decisions to favour single-threaded performance, which would not be possible if every core was treated equally. The next thing was to look at thread migration. And this is where things like the quality of service APIs can be really important to ensure that long-running background tasks are treated as such. The other thing to bear in mind is that as hardware scales out with more and more available cores, the game's tasking system overheads could potentially start to increase. One thing we looked at carefully in Hitman is why we go as wide as possible for things like the physics system. There are times when we actually deliberately limit the amount of width we place in the tasking system. So we have one thread running per physical core. This means, especially given the benefits of reduced SMT utilization, things like the control and render thread spend more time with their own dedicated resources. So at that point, I'd just like to hand over to Alessandro from IO Interactive.
Hello, my name is Alessandro and I'm here to talk a bit about more the implementation part of ray tracing in Hitman 3. Before we start diving into the details, let's show you some results. So Hitman 3 is a title released in 2021, but the content in the game that includes something like 20 plus levels has been built since 2014, something like that. From this talk, I'm going to talk most about the ray tracing and the ray tracing reflections, with a bit of talking about the ray tracing shadows at the end. Let's start. So Glacier is our engine. It's an in-house engine and is a tile deferred renderer. So as in classic G-buffer rendering, you pre-render the G-buffer of the scene. You create some lighting result based on the different lights you have in the scene that are cached in the screen in different tiles. Finally, you render with forward lighting, transparent and emissive objects. And at the end, you apply some post filters and synthesize the final image. So when we were designing ray tracing, or how to implement ray tracing in our engine, we had some main design principles. So the main thing is that we want to reuse as much data as possible. So most of the materials and the geometry that is already available in the engine must be reused. We had limited content optimization. As I mentioned before, we had 20 plus levels in our game, so we didn't have the time to go through every single level and modify every single piece of geometry. I wanted to reuse the existing system of the US. So the existing reflections, the existing culling system, and I will talk a bit about them later when I talk more in detail about the reflections. So what do you want? What do you need if you want to do ray tracing? So in my mind, I divide what you need for ray tracing into three main categories. The first thing you need is ray tracing shaders. So any hit causes hit, generation shaders, and mist shaders. So any hit causes hit are the main shaders. Any hit define the geometry. So if something has been hit or not, especially for stuff that has alpha tests. Closest shader is the actual shading that defines the final shading result of your ray tracing algorithm. And then you have a regeneration shader that schedules the ray, and a mist shader that handles the case when you don't hit anything. The second big category is acceleration structures. So basically, in ray tracing, you divide your geometry into separate entities. This is not something that you only have in ray tracing to accelerate your ray traversal. These individual geometry accelerations are called BLAS or bottom level accelerations. And then on top of that, you basically build a scene visualization of your bottom level acceleration, which is called top level acceleration or TLAS. Finally, ray tracing as a global state. So you actually need to bind, when you're tracing your rays, all the global state, which can be constants, so parameters of your materials, some textures of the different objects that you're rendering, and of course vertex attributes. So your normals, your UVs, all the different stuff that you need to actually fetch the different attributes in your geometries. So let's start with the first category. Ray tracing shaders. In Glacier, shaders are defined via graph. So artists have complete freedom to decide how different objects are lit. So artists create the shaders and they output the different lighting parameters to a node. Each material in our engine must be define a pixel shader, but can also define a vertex shader for some special effect. So if we look at this diagram, which is basically the graphics pipeline, I illustrated in yellow the code of the two shaders I just discussed, and in blue the fixed function that actually goes around them in the graphics pipeline. So we have an input assembly that provides inputs to the vertex shader that generates the final triangle position as we position in normalized device coordinates that then gets fed to the rasterization algorithm. The shader can also generate parameters that are then interpolated with the barycentrics provided with the rasterization, the fixed function, and then are fed to the pixel shader code. The pixel shader code leads the individual pixels and then outputs the render output unit. So if we have these two shaders, how do we actually convert them to a natural ray tracing shader? So to actually convert them to a natural ray tracing shader in this other diagram, we actually need to actually do way more work, a bit more work than is actually necessary in the rasterization. So of course, all these parts that we get for free in rasterization, they are not in ray tracing. So for example, from ray tracing, we get a primitive index that we need to use to fetch our geometry in a step that we call input assembly emulation. Then we can actually feed this result to the vertex shader code that creates the parameters. Of course, the parameters are not interpolated automatically. We need to interpolate them ourselves. Luckily, ray tracing provides barycentric coordinates. Once we interpolate them, we can actually feed them to the pixel shader code and finally store the result. Of course, don't have a render target in ray tracing. We can just use a UAV storage. Right. So before I go a bit more into detail how these shaders are actually constructed, I need to distinguish between different kinds of the geometry that we have. So for ray tracing, in our implementation, we distinguish geometry in two types, and I call them simple and deformable. So simple geometry basically is geometry that doesn't change throughout the level. So it doesn't get basically deformed across the level. So it can still be translated, rotated, and scaled, but the actually structure of the geometry is always there. And I write available vertices in the sense that the vertices of this geometry are already available in our attribute buffers. For deformable geometry, these vertices are not available because they actually are generated on the fly by the vertex shaders. So these shaders can be bone animation, custom vertex shader, non-standard vertex layout, or cloth. This kind of vertex shaders are very much more complex and they need a special handling that we will discuss in a second. So let's have a look how we generate any hit shader for simple geometry. The closest hit is very similar, so I'm just going to focus on the any hit here. So we take our vertex attributes buffers. We have position, normal, vertex color, whatever you need. We fetch them with this input assembly emulation and then feed them to the vertex shader code. So that's the first thing we do in any shader. Of course, as you can see, we have to run this code 3 times because the AnyHit shader operates per triangle and not per pixel as the pixel shader. Then we actually run the interpolation manually and then feed the result to the pixel shader code and actually, in this case, clip or call ignore hit depending on the result. Of course, if you have a closed shader, we do something different depending on our implementation. For the formable geometry, everything is a bit more complicated because we actually need to output these positions for the acceleration build. You can see them in the center of the image in that object space buffer. This is the position that will be fed in the bottom level acceleration build that I will discuss in a second. So we need to split everything into two different parts. The first part we call it vertices compute. This part actually fetches the input assembly emulation and then calculates the vertex shader code and then stores it in these two different buffers. The object buffer that I just discussed and this intermediate parameters buffer, which are the parameters that are going to be interpolated later. The AnyHit shader just fetches these parameters, interpolates them, and runs the pixel shader code. So it makes it much more simple from the AnyHit shader point of view. We will see that the AnyHit shader has a bit more complex bindings, so simplifying the bindings for the AnyHit shader is quite important. And as normal, we call ignore hit, and that will be it. So this is now that we kind of discussed the pipeline for generating the shaders, let's go back and talk a bit about the bottom level acceleration build. For simple geometry, it's very simple. We have the vertex attributes. As I mentioned, the geometry is already there. We can just basically build this straight away and generate already a BLAS in the BLAS heaps. DX12 Raytracing offers another option called compaction, which is basically reducing the memory impact of the acceleration structure. We actually do it straight after at the beginning of the level as the build so that we can just save memory. It saves like around 40% of memory, I think, on NVIDIA cards. Right, so this is very simple. Of course, we can do it at the beginning of the level. For the formable geometry, we need to do it every frame because the geometry can change every frame. Think about it like bone animation, right? So as I mentioned before, we have this vertices compute buffer that outputs this object space buffer. And basically straight from the object space buffer, we can actually call the build or update function. So build, just build acceleration straight away. Update reuses the build result from the previous frame to update with the new positions, and that actually is much cheaper. We will see later how we actually split these two depending on the performance. Right, so this is the first two ingredients, as I mentioned, to do ray tracing. The third ingredient is the bindings. So in DX12, DXR ray tracing, we need to define the bindings via a shader table and a local root signature. So a shader table is actual memory that gets allocated with the different pointers to these different bindings, and the way we define these bindings is via the local root signature. So in our engine, the local root signature is fixed and it's made as the image that you see in the center. So we have a it group identifier. This is mandatory. It's basically a pointer to the shader, if you want to call it about it. It's 32 bytes. It's opaque from the API and kind of identifies any hit plus closest hit pair. Following this 32 bytes, we have another 32 bytes that define 4 bindings that we actually use in our engine. And as you can see, the bindings are registered in space 1 because we actually have to not overlap the existing global root signature, which is in space 0. So the 4 bindings are, the first one is called a material const buffer that defines all the material constants and all the textures that are defined by the material. And these are actually pointed in bindless so that we don't have to create bindings for each one of them. The second buffer is just a const buffer that defines per object data, so like matrices, scaling parameters, all this kind of stuff. The third one is a geometry const buffer that defines the geometry attributes and pointers to a bindless buffer that stores the vertex attributes. As you had mentioned before, simple geometry has to fetch this one, and then deformable geometry has to fetch the intermediate parameters. So we actually have to fetch it with an SRV that we bind to T0. We could actually, in principle, compress all these constant buffers into one, but actually the shader table must be aligned to 64 bytes, so we won't gain any memory, and this is actually a bit simpler to implement for us. Right, so now let's have a look at what happens actually in the lifetime of a frame in ray tracing. So I created this graph, as you can see in the image, that basically shows all the data dependencies that you actually need to run ray tracing. So in the top part, we have all the data that you need to build an acceleration structures. And the middle, you have the 4 bindings to the shader table that we just discussed. And then at the end, you have basically the actual code of the shaders, the anti-heat, closest heat, regeneration, and mist shaders. So the first thing we do, a level load, is basically initialize these vertex attributes and texture heaps. These are actually shared, as I mentioned, with the normal graphics pipeline, the rasterization pipeline. So we actually don't need to do anything there. They're just uploaded for free, basically. And also the shaders are streaming as basically as the level loads. So we actually basically collect them during the level and then build the pipeline once at the beginning of the level, and then we are basically done. So we actually build this RTPSO, ray tracing pipeline state object, and then use it for ray tracing. All right, now per frame instead, the first step we do is having some sort of bookkeeping. The idea is that we have these instance buffers that are actually the data that are per object, and we actually update them in a sparse way depending on which objects have been moved. So we actually basically update this instance constant buffer and then instances at the top, which are something that we need to build the top level acceleration structure. And we actually update the shader table as well. So we actually use a compute shader with sparse copy that just updates what we need. After this small bookkeeping step, that is very cheap in general, we run the vertex compute, which is basically just a modified draw loop that basically fetches the vertex attributes, run a compute shader that emulates a vertex shader, and then writes the final position data on the GPU. This is running multi-threaded, like all our draw loops, and it's kind of more expensive actually on the CPU than the GPU, I would say, but then allow us to write the position data. This position data, we actually feed them straight away into our BLAS build. We actually compact all the builds into once for better performance. And actually, we don't run this in multi-threaded. We actually collect all the acceleration builds into a single command list and run it at once, because this gives us much better performance. As I mentioned before, we can choose when we build. We can actually build or update an acceleration structure, and this is based on the LOD and which frame we are. So we actually have a certain build update ratio that we can maintain for performance. The final step that we do is the TLAS build. This is done using a pointer buffer, which basically is pointer to this other instance buffer. Instances are what connect the shader table and the BLAS, basically. We do this with this pointer buffer because with this instance buffer are updated via sparse copy. So we actually don't need to actually update all of them at once. All right. So that was it for the core ray tracing part. So let's talk a bit about details about the implementation of the ray trace reflections. So let's start by reflection in Hitman 3. The first kind of more important, I would say, reflection algorithm that we have that was introduced actually in Hitman 3 is a screen space reflection that give us already a good result in the reflection. But of course, they have their own limitations because they cannot reflect whatever is on the screen. Then in Hitman, we also have something called planar reflection, which is basically a camera that renders a plane from the opposite side of the wall and then applies it as a reflection. It's kind of an old trick, works really well, and we use it for a lot of planes like floors or glasses in our engine. Then, of course, we have box reflection fallbacks that actually, just as it is, just can give you a static reflection when everything else fails. And then now on top, we have ray trace reflections. That is our new introduction that improves whatever we have. So, as I mentioned, the ray trace reflections actually update the existing screen space reflection. So they are a hybrid system. As you can see on the right image, these are what we get if you have all these screen space reflection. You can see towards the bottom of the image, the reflection cannot get on top of the screen, so they cannot visualize basically what is what is reflected above that pillar, basically. If we show the result for ray trace reflection, of course, we get a much better result that actually shows a much more realistic effect. So how do we do this? So there's many steps, of course. The first and most important step for performance is something called trace scheduling. So basically what we do is we generate, in this case, visualize an image, a set of directions per pixels that decide where the ray is going to be traced. And this is based on the reflectance. So if something is very rough, we don't trace the rays. And also we have this thing called a reflectance bump that actually makes the lines aligned better together, so they can actually give you a better performance. And of course, this decides if a ray, if something has already been traced correctly by the screen space reflections. So we can actually reuse the screen space reflections result when available. So after we have scheduled these directions, we can actually feed them to the ray tracer, and what we get on the other side, of course, is something called a G buffer sample. So once we hit a surface, we actually convert the existing G buffer shaders that we have into actual ray tracing shaders, as I described it in the previous part of the presentation. This return 4 different samples in our case with the 4 different G buffer samples. So we have a diffuse, specular, normal, and specular power. These 4 inputs gets actually fit together into a lighting algorithm that actually creates the finally lit result. So how does the lighting or shading algorithm work? So it's based on a workspace data structure, is a workspace grid based, and it's similar in space as tile deferred. So basically, in tile deferred rendering, we can only light whatever is on the screen because the light collection happens only per tiles on the screen. While in ray tracing, you actually need to light stuff that may be behind you, so you can actually not reuse that existing stuff. So we actually need to make a new data structure that actually caches the lights in workspace to actually be able to light a single, basically pixel or single ray that you actually cast. So a bit more in detail. So the diagram shows in 2D basically an idea of how our system works. So we have actually, in our engine, we have the concept of rooms, which are the blue rooms, and then there is an outside which is in green. So we have different rooms that can be that are defined by artists, and they actually allow us to do better culling, portal culling, all this kind of stuff. So those are already available. We have Hitman, or the camera, in the center of the screen. And then we have different lights. So of course this is simplified. We only have 2 lights here. We have thousands of lights in the actual game. But the important thing to show the gist of the algorithm is that we have a set of lights, each one with an area of influence. So once we have these lights and each one with its own area of influence, we actually overlay our workspace grid on top. So it's a workspace grid that actually becomes more and more detailed the more you get farther from the camera. And in this workspace grid, we can actually cache the lights. So you can see in the next image, each cell of the workspace grid has cached the information of which lights are in there. Right, so now let's say we are in this situation. So Hitman sees, or the camera sees the red dotted line. That's the depth buffer. We fetch the depth buffer, we cast the ray, which is kind of white. We hit the point at the end of the white line, and then we want to shade this point. So basically what we do, we go in the workspace grid, we fetch which lights that we hit, and then we compare them, and we kind of decide based on the lights in which room they are, and we shade based on the different room in which they are. These avoid light leaks, and in general give us a good shading result. Light. Now we have the output from our algorithm, which is the lit result. Of course, the lit result is noisy. So because of course the rays have some randomness to them, that can also be temporal. So as you can see on the right image, this is the final image without any denoiser. And of course, in our implementation, we actually apply a denoiser, which we use the NRD denoisers from NVIDIA, relax or blur, depending on the actual quality settings. So as you can see, the image now is without denoiser, and this is with denoiser. And in the inset, you can actually see like an inset to see better what the denoiser does. So as you can see, it actually improves quite a bit the noise and also in the temporal space, and that allow us to actually give you a nice denoised image instead of the noisy mess that it would be with the normal ray tracing. We also add support from transparent objects. So transparent object render basically depth and normal, and we use this depth and normal to actually start ray tracing from transparent objects. We assume that transparent objects have unit reflectance to avoid denoising the actual result of this, and that actually seems to work well for our engine. So as you can see on the right image, that's the result with SSR plus box reflections, which works okay. But if we see the result for ray tracing, you can see that the actual table gets in the reflection, so that will be a bit harder to achieve without a specific box reflection. And then, of course, the result is much more accurate, and we can actually see a dynamic object moving in the actual reflection, which will be the lady. I don't know if you can see it, but if you actually play the game, you will be able to see it. Right, so now we have the idea on how this ray tracing algorithm works. Let's have a look at performance, just very briefly, for 3 views. It actually some of the 3 worst views in the engine, I think, for our performance is were captured on NVIDIA 3080 at native 1080p. And as you can see from the image, so one of the main loads, of course, in the frame is the trace in the center. Of course, also the BLAS and TLAS updates is not insignificant, but those can be hidden in async compute. So we actually do that, and they are basically run at the same time as the gbuffer fill. So we actually don't need you can eat basically part of the performance. You can actually gain some performance out of that. So as I mentioned, also the workspace lighting is not insignificant depending on the scene. Of course, for big open scenes as the first one, it's very, very significant. But then, of course, in general, we get a good performance out of it. Finally, we have the denoising, and the denoising, yeah, just a certain percentage of the frame as well. So as a final thing, I would like to talk a bit about some of the optimizations that we did to actually, some of the most significant optimization we did to actually make ray tracing work. And the first one I want to talk about is called Simplified lighting. So in general, in our engine, our artists have the possibility to select something called shader LOD. So they have 2 levels of LOD for the shaders, and that's a high quality shader and a low quality shader. And basically the idea is that they can blend this with distance. So actually for far stuff, they can have a slightly cheaper shader, basically. In ray tracing, we actually just use the simplified shader because it's just reflections in general, and it's not super important that the shaders runs at the full possibilities. So as you can see from the top row, we have the normals, and the normals in the simplified, for example, they don't have the bump mapping. All the diffuse doesn't have the blending of multiple textures, all this kind of stuff. So in general, that this was a very significant optimization that we actually used in our engine. The second huge optimization that we use is culling. So as you can see from the center image, we have a camera, which is basically where Hitman is, and then around it we have a set of geometry that looks a bit weird. That's basically a debug geometry that shows us which geometry are we actually using in the culling. So you can see everything outside of that, the room source of that, are being culled by the rasterization algorithm. Of course, with reflection, it's not as simple. You cannot just reuse the same culling result because reflections can go outside the current room that you are. So what we have to do is actually slightly expand this culling box. And you can see that's the red box is the actual one that is used by the reflection, so it's much bigger. And that allows us to actually still use culling with reflections, but actually still get some performance gain because we are basically putting way less geometry in the TLAS. And as you can see from the TLAS, that's the actual visualization of the TLAS on the right. And that's actually much less geometry than the whole level. Of course, it's still significant and there's still a performance problem, of course, but it's way less than it would be if we put the whole level in the TLAS. The final optimization I want to talk about is content. I mentioned we had limited content optimization. Of course, we have some content optimization in the form of removing objects. So as you can see on the top, the main image shows the final frame in the rasterization, and the inset shows the raycasted normals, which is basically the normal, what basically the ray tracer sees. And you can see there's way less blends in the raycasted normals compared to the main frame, and the idea is basically that artists can go through for the worst case and remove some objects that are not very visible in the reflections. All right. Finally, issues and improvements. So as is the classic thing with the SSR blending with RTR, we have some potential blending issues. So as you can see here, of course, the lighting, it blends okay, but is not the same between the screen space reflection and the ray trace reflection, and that's something you kind of have to live with because it won't never be the same lighting as before because of course SSR samples the result from the previous frame. Of course, as I mentioned, there's limited content optimization that we can do, so the content is not as optimized as it can. We try to handle the worst cases, but yeah, it's there's still some work to be done there, but unfortunately we cannot do it in the time frame we had. Of course, especially at low quality, there are some small popping artifacts because the lower quality has way less stuff in the reflections. but in general, we think we did a good work to limit those. And finally, of course, Raytracing doesn't support everything. We didn't add emissive and transparent in Raytracing for performance reasons. So we actually would like to do that in the future, if possible. All right. Before I finish my presentation, I would like to talk briefly about Raytrace Shadows, which is something that will be available in our implementation. It was kind of the stepping stone towards Raytrace reflections, basically, but we decided to leave it in the game as well. So the Raytrace reflection in our game are single light. There is only one light that we can use for ray tracing, and it's only for the sun and the moon. The implementation is similar from the ray trace reflections, but in this case we don't have a closest hit, and we just accept the first hit, which allow us to actually make the ray trace shadows much cheaper. And on top of that, we don't really remove the existing shadows. We actually just refine the existing result. So you can see this is our standard shadow for the sun, which is a cascaded shadow map. And if I show you the Raytrace shadows, you can see that the result is a bit better. We get some better contact hardening and some better overall more simulated area light effect, basically, because actually Raytracing allows us to simulate an area light for the sun. So this is the before and this is after with the Raytrace reflection. But yeah, with this I would like to conclude my presentation. Hitman Raytracing is coming soon. It will be released very, very soon in our next patch.
Thank you, Alexandro. So, for the final part of today's talk, I'd like to cover Intel's XeSS, a machine learning approach that delivers high performance with exceptional image quality for upsampling. To phrase the basic problem, game developers have to constantly balance the need for increased image quality with rendering performance. High-resolution displays and new rendering techniques such as ray tracing that we've just covered further increase the per-pixel workload. There are a range of traditional approaches for upsampling, but they each come with their own set of trade-offs. The goals of XeSS are to allow a significant performance increase, suitable for upsampling from 1080p to 4K, while maintaining the original image quality even with a scaling factor of 2x. In addition, the idea is XeSS is a generic solution that does not require any per-title training. XeSS fits in directly where the game's traditional TAA stage would actually normally be applied. It comes with a range of different quality presets that with a different set of balances between performance and image quality. In terms of the expected uplift, if you compare a game rendered natively, where everything from scene rendering to post-processing is done at exactly the same resolution, a traditional upscaler would probably render the scene and post-processing and the TA at a low resolution before doing a final upscale pass before the UI, giving a very significant performance uplift. XeSS actually fits in directly after the scene rendering, but before the post-processing. This improves the image quality, but does mean the performance uplift will be slightly less. In terms of the expected uplift, it really comes down to that the cost of the scene rendering at the scaled resolution plus the cost of applying XeSS, which will vary depending on the image quality settings, is less than the native scene renderer. For a title like Hitman, that has a very high per pixel cost, the gains can be significant, but it may not apply equally to all titles. Looking at the rendering engine integration, XeSS has a minimum set of inputs each frame. We have a jitter offset that's applied to the main scene rendering. We also have the input texture itself, both in standard definition or HDR ranges. We have an optional exposure texture, high resolution dilated motion vectors, and the resolution controls. Alternatively, and this is what we actually use in Hitman, we can pass the low resolution motion vectors plus the depth buffer, and XeSS will do the scaling itself. As an output, we have our upsampled pre-tone mapped output texture, plus potentially the history buffer can also be reused. That may be useful for things like screen space reflections. The jitter itself needs to be a sequence of at least 32 frames in the range of plus or minus 0.5. This can be directly applied to a projection matrix's shear transform, but needs a scaling by a factor of 2 to place into NDC space. This did actually catch me out when I first implemented it in Hitman. The other thing to bear in mind is we need to apply a bitmap bias when rendering at low resolutions. This ensures that the game is actually using the same texture bitmaps when rendering the scaled image as it would have used for the native. Otherwise, the high fidelity detail is simply not there when we try to reconstitute the image. Looking at Hitman 3's XeSS integration from a slightly different point of view, you can see here the scene rendering with the jitter applied to the G buffer is done to reduce resolution. Likewise, we can also reduce the resolution of the shadows. We save on things like screen space ambient occlusion, which is done at the lower resolution. Our ray tracing costs, all of which generate our final 3 textures that we pass into XeSS, being our low resolution velocity, depth and image. With the exposure texture applied, XeSS then upscales to give us our pre-tone mapped 4K image that we can then pass through the rest of the post-processing stage. Because we're using the low resolution motion vectors and the depth buffer, it effectively matches the game's own TAA inputs, so there's no additional pre-processing required. The one thing to note is the velocity itself does have the jitter removed. Looking at the integration from a slightly different point of view now, the default behaviour for XeSS is to just pass in the D3D resources for those primary input textures. XeSS then allocates internally its own temporary textures, constant buffers, and creates its own descriptor heap that it itself manages. On return from XeSS, the app is responsible for restoring any state and binding any of its own descriptor heaps, because they will have been changed by XeSS. Hitman 3, we're looking at a slightly different approach. XeSS also allows you to return a lot of the properties to find out what resources it needs to create. One thing you can find is the number of descriptors. We find that and then allocate double that space on the game's own descriptor heap. Then when we come to call execute XeSS, we pass that heap plus an offset which we toggle each frame. XeSS then populates that with its own descriptors, but on return we no longer need to actually reset the heap because we're still using the game's own descriptor heap, and that saves a pipeline flush. If we move on to actually look at the quality we're getting from XeSS, this is an image taken at 1080p and then upsampled to 4K, and this is already scaled by a factor of 2 as I'm only showing part of the same image. This is what the image would look like at that 1080p with nothing else applied to it. You can quickly see that the game's own TAA does a very good job of improving the actual quality. If you look at that next to 4K, you can still see that 4K adds significantly more fine detail. And looking at 4K relative to XeSS, you can see we've actually done a good job of capturing the quality. Probably the best thing to do is to actually pick a couple of small sections of this image and zoom in closer. So I've picked 2. One is the tiles on the floor, and one is the actual metal beams that actually support the glass. Looking at the tiles first, the thing to be actually looking at is the line between the tiles just beneath the people's feet. You can see that the real difference between 1080p and 4K is we have a very defined line with a specular highlight. While the TAA upsampling does a good job of smoothing out the line, it doesn't pick up the actual specular highlights, where XeSS does actually do a very good job of picking that up. Looking at the metal frames, again, comparing the TAA, so the 1080p to the native 4K, the real difference here is actually in the lines of the wires that support the glass in the background. And you can see that XeSS does a very good job of capturing almost all the detail from native 4K. The other thing to bear in mind, it's not just about the quality of the image, it's how much performance we're gaining from this. So looking at those 4 different ways of rendering the image and comparing costs, you can see that native 4K is a little more than 2.5 times slower than the 1080p. The game's native TA solution does a very good job of upsampling while maintaining a very good performance, where it's almost 2.5 times faster than native 4K. The big difference here is comparing 4K XeSS to native 4K. XeSS is more than 2 times faster, provides almost all of the image quality you get from native 4K. So it's a good example of how we can actually maintain the actual quality that we would have, but get most of the performance benefits of actually rendering at a much reduced resolution. And that pretty much covers everything for XeSS. So finally, to wrap up today's talk, Hitman 3 makes heavy use of both the CPU and the GPU. CPU optimizations are still incredibly important. Moving Hitman 3 to Intel's 12th generation core meant looking at how the game would play with the hybrid architecture. The two main things we looked at was ensuring that the game's critical threads, the control thread and render thread, both ran on the P cores. And we looked at the performance on the P cores, especially the bubbles. And we went wider inside the tasking engine to make better use of the E cores that we had available to us. Looking at ray tracing, as already described by Alessandro, the game has added a great deal of detail. It does come at a performance cost, but by mixing a hybrid approach with the game's original screen space reflections and adding AI-based upscaling techniques such as Intel's XeSS, we can maintain high performance or bring in high quality visuals to 4K for Hitman 3.